Welcome back, everyone. Hope you enjoyed the lunch. So we are back on track with Maria that will, from IRIA that will present the symmetric cryptanalysis, state of the art and future. Thanks, Maria.
Thank you, Emma. And I would like to reiterate what was said this morning. Thanks a lot to all of you for being here. I think it's super nice to see that many people interested in this topic because we think it's a very important one. Yeah, sure. Thanks. And it's nice to see that many other people are also interested. So what I'm talking about now, it's going to be mainly my point of view, which is also one of the main topics of my ERC So Basic now. And so it's kind of a personal point of view of what I think should be done before reaching like the full automation that we need to obtain in the end. So it's much more an algorithmic point of view than implementation-wise. And I'll try to explain a bit the context of also the following talks that we're going to have. And I wanted to say sorry because I'm not citing any papers besides differential cryptanalysis, because I started citing and there are too many things and I was forgetting things and I didn't want to. So I'm only citing the talks that are coming after. So this morning we have seen that, I'm repeating a bit what I just said, some of the most popular existing tools for automated symmetric cryptanalysis. And this afternoon, and also Jose's talk, I think it was a little bit more related to this. We will see some recent results and open problems that are contributing to the cryptanalysis automation that we all want to reach. And so I will kind of try to give a kind of the gap between these two parts and the context of where all of this is placed in my point of view. And it's not a technical talk, so I'm sorry for that, but maybe it's more relaxing for you also. Yes, that way you can have a siesta and it won't be very important. So, well, that you all know that symmetric cryptography, if you're here, you're convinced it's super important and we need it to secure communications efficiently, and it's widely used. And the modus operandi of cryptography, it's mainly people propose design of primitives that answer certain needs that appear. And then in order to trust these primitives, the community cryptanalyzes these constructions and try to find attacks. And so they do this by trying to apply all the known attacks on these new primitives or by trying to discover new attacks. And so the more a primitive is cryptanalyzed without finding any problem, the more trust we can have on it. And if we cannot break it, then this modus operandi allows us to define a security margin. How far is the primitive from getting broken? And so that's very nice. But I think that in the current situation, we have a problem. And I think there are many serious drawbacks that I will list later. And maybe the most important one is that it's impossible to efficiently check if a primitive resists to all known attack techniques. So this is a very tedious work. So each time someone proposes a new primitive, you need to test a lot of things. There are a lot of tools like class that help you trying some of the known attacks and finding some best distinguishers, but that doesn't apply to all the known attacks and techniques. And I will try to explain why this is difficult and it has not been done and what I think we should do in order to counter this. So for understanding how we got here, I think it's, for me at least, Patrick doesn't agree, but it's very important to understand that in the last 2 decades, we have had many recent competitions for finding new standards and or non-official competitions. And there have been many new needs. And actually trying to count, I think there are many more, but we have seen appear more than 200 new symmetric designs, which is very big. And this has implied a huge amount of new ad hoc cryptanalysis results. They are cryptanalysis that are using already known families of attacks with some new variants, with some new ideas, and also new families of attacks have appeared in this last decade. And so this is a lot of information that I think is very hard to compact and to really assimilate. And so this competition context that is very nice and everyone was very happy about it and it motivates a lot the manpower of the community for contributing to this, has some problems. It's because normally these competitions have like a limited amount of time, like for instance 5 years, and they are composed of rounds. So if you're working on a primitive and you find a result, you're breaking something, you really want to publish it before the next round appears, because otherwise maybe your result will be less valuable. And so and also a lot of people are working on the same thing, so it's very competitive, and it has happened many times during these competitions that some people had a result and some other people publish something that is very similar, and then it's kind of wasted work, and that's a pity. So that's why everyone was like in a hurry of producing new results, of analyzing all the primitives. And then we didn't really have the time to stop and think and try to understand what we had proposed. And all this urgency, I think that it's a paradox a bit, that it implies a waste of time in the long term. And some of the problems of this is that I think that, as we said, we don't really, we are not able to analyze efficiently the risk resistance of a primitive against all known attacks. That means that sometimes we can have a low security of new designs that can even sometimes get broken by known techniques, because maybe a variant that existed was not tested by the designers, and actually when you try to apply it or with a small idea, you can improve the complexity. And this happens sometimes, and I think that's a problem. And also sometimes, quite a lot of times actually, too often, from my point of view, some published attacks are incorrect or are non-optimal. It happens with my papers also. I mean, it happens a lot. And for instance, in possible differential attacks, there were a lot of results that were published, and actually they were not correct. Or rebound attacks weren't optimal because some steps weren't doing correctly. And that's a pity, because then we are basing our trust in the primitives on things that are not correct. Then all the modus operandi that I presented in the beginning doesn't work if the results we are relying on are not good. And this also maybe is less important, but I think it's still representative of what a problem this is that many techniques get rediscovered or renamed. So a lot of times there's a paper, and I have done it also when we proposed conditional differential attacks, or came and said, actually, Eli Bingham already proposed something like this a few years ago. I never managed to know in which paper, but so I think it happens a lot. So, but it's not because people don't do it correctly, it's because I think it's very complicated to follow and to track all the things that have appeared. And so I have tried to explain why I think this is a bit chaotic, and this could be changed and it could be improved. And I think the way of doing this is to take a step back. And for this, a first objective that is related to what is the main topic of the workshop, that is finding automatic tools for performing cryptanalysis. I think that a first objective for reaching the long-term goal that I think we would all like to achieve is to proposing a generic algorithmic framework that will capture all variants of non-cryptanalysis techniques. And this has been hard, as we said, and the main reasons is because most of the times what we obtain or what we publish are ad hoc attacks against specific primitives, and it's very complicated to propose a relevant generalization or formalism of this attack, and also to understand and define the underlying algorithmic problems that could be solved more optimally, actually. And this first objective, I think, would be very important for the final ideal that I already said, that would be including all these algorithms that would be now easier to implement and to analyze and to optimize into an open cryptanalysis platform. And for this, you will see Thomas talk in the end, or for like a security benchmark for security primitives that would be a toolbox including all the best known attacks and algorithms and ideas and variants. And this is like an utopia, right? So I will explain a bit more about what I think it's really doable in the end, but that would be the ideal goal. And so we have already seen in the morning some very nice talk with very nice and very important efforts proposing tools that it's really important and really interesting now. And these tools also have some drawbacks that I think we can all work on trying to. So that's normal. It's the evolution for reaching automation, I think. So a lot of times tools are dedicated to concrete attacks or even a concrete step of the attack or concrete ciphers. And normally generalizations are applied on isolated steps or include heuristics that are not really realistic or that don't allow to obtain optimality. And because of the chaotic situation that I mentioned before, many of these tools don't include a lot of existing improvements that are very hard to really understand or to really see the full potential of them, because it's very difficult. And also they are kind of hard to use sometimes. So CLASP, I think it's much easier. You had a tutorial of how to apply it this morning. But the thing is that they are not at least for now, they are not systematically used by designers when proposing new designs. And this is a pity. And I think Maria's talk will maybe mention this a little bit more, right? Or yes. Okay, so now I will try to explain like the general, very simple thing I think we should do. And for reaching this generalization, we will go from ad hoc attacks to generic and from approximative complexities to more accurate. So we'll start with the actual state-of-the-art cryptanalysis situation that is very technical and ad hoc, most of it. And we will try to perform a generalization of this using an algorithmic approach that I will detail a bit more later. And this approach can be constantly improved with new optimizations and new ideas that we can find and that we can try to apply. And in the end, once we have these generic algorithms that are optimal, we can use them to be implemented on a software toolbox that will allow to automatize fully symmetric cryptanalysis. So that's like the objective that I think we all want to reach, like an all-inclusive, easy-to-use toolbox. And as I said, many preliminary steps have already been done in these directions, but there are many left. And so this talk is mainly about what I think it's very important, that is this middle step here, for being able to do a very good and an easier and a more performance automatization in the end. So the generalization step, so it's not even very clear in my head how it should be done. So I try to separate it and dissecate a bit the different parts that when we try to apply it, we do. And so I will just try to give like the roadmap of, I think, how should people try to do this kind of thing. So we start from a concrete existing attack on a concrete primitive. I think it's good to start from something very concrete. And then we try to provide an operational representation. I will give an example later with differential attacks. And once we have this operational representation, it's often easy to propose the approximated complexity of an attack using this representation. Sometimes we need to introduce some known natural parameters that will help us, like put a parenthesis in a part of the complexity that maybe is super complicated to write down generically. But as in the operational representation, we have defined the parameters that are important for the complexity. Normally, this step is easy. And actually, we will see later that these two first steps have already been done for some families of cryptanalysis. Another part that has also been done, but is much more rare, is once we have done this, see very clearly which are the different steps we have to apply in the attack, because there are most of things represented by the terms in the approximated complexity. And we can identify sub-problems that appear there that are not solved optimally. So we can try to find better ways of solving this, and this may allow us to optimize one of the terms of the complexity. And with these two parts, we can try to combine them to obtain a more accurate complexity in the end, by making a substitution of the complexities we had before with the problems that are now better solved. And in the end, it will give us, we hope it will give us an optimal algorithm in order to be able to implement it for finding the attacks. So I will just give a brief example about generalized differential attacks, which is a very well-known family of attacks that I'm sure you all know, that was introduced in 1990 by Biham Shamir. And even though it was introduced so long time ago, I think there are still differential attacks that get published that are not optimal, and still new primitives that get proposed get broken by differential attacks or variants from them, which is, I think, very representative that even possibly the most well-known family of attacks that we have, it's even not that well-known, actually, when we take into account all the things that have been proposed. And so if we consider these kind of attacks, we can, so as Jose discussed this morning, most of symmetric families of attacks are composed of two parts. So the symmetric primitives, most of them are iterative, so we can They are composed by the application of a similar round function that is parameterized by a part of the secret key and a round constant. And the attacker tries to recover the secret faster than brute force. So in most of the attacks, we have 2 steps. And finding the attacks is a very tedious procedure that is often done in 2 separate steps, though the steps are not independent. But the best we know how to do it and how to implement it, we don't know yet how to combine or how to propose an algorithm for obtaining the optimal attack, considering both at the same time. So the first part is something in the middle, for instance, finding a distinguishing property in differential attack that is an input difference delta in that goes to an output difference delta out with a higher probability than in the random case. And then this distinguishing property can be extended some rounds in the beginning and in the end, such that if we guess the correct key that appears in these rounds, we can detect the distinguishing property. And the thing is that we don't know how to implement something that will find an optimal configuration for both steps at the same time. So what happens most of the time is that there are tools that can find some good distinguishing properties, and then mainly in another very way, we extend it with a key recovery phase. So let's see what exists now regarding automation of differential attacks. So there's a part of finding a distinguisher that I said before. So there are a lot of tools that exist using MILP or CP or SAT solvers that find the best distinguishers for a given number of rounds under some heuristics. And for instance, we will see later Xiaowei's talk that talks about this kind of tools. And there are also some other tools that, given a distinguisher, they try to find the optimal key recovery. And so there's nothing that is really generic for this, but in some concrete cases, there are some tools that exist. And for this, for instance, you can see a link stock that will come right after mine, that is talking about a key recovery tool for word-based ciphers, right? So, and then we have the most important question that we should solve, which is finding the best overall attack, because the thing is that best distinguishers don't forcefully imply best attacks. And so this question is not solved. There are some tools that partially include with some heuristics, for instance, regarding the lower bound of the key recovery complexity, which can be given with the number of solutions that they have. And for instance, in Jose's talk this morning, we saw this being taken into account, or more evolved heuristics taken into account in the attacks that were implemented. Or on Patrick's talk later, even though the main objective of his talk was improving the distinguisher of impossible differential attacks, they also use this lower bound to check what would be the final complexity of the attack in the tool that they implemented. So the question is that an algorithm providing the best overall attacks doesn't exist. And I think that's because first, we should really perform correctly the generalization of this kind of attacks in order to implement the algorithm that we would obtain in a tool that would allow us to then find them. So just a very short, it's not very detailed, but it's just, I think when I talk about the generalization step, it's a bit abstract and we don't understand very well what I meant. So just to see what I mean with the different steps regarding differential attacks. So if we consider operational representation, it's the one that we can see on the slide, where we separate the different parts and we include all the parameters that will be needed for defining the complexity, or the time complexity, or all the complexities that will be associated to this attack. And once we have the operational representation, it's easy to see what is the approximated complexity. So in this example, for instance, we have the first term that is related to the data generation that we need to perform the attack. The second one is associated to, once we have the data generated, how to build the pairs and how to sieve them to only keep the pairs that verify certain conditions in order to be candidates for verifying the differential path. And the last term, it's the one associated to the key recovery phase. So in order to write this formula, we had to include, for instance, CS, which is a very non-natural parameter, I think, that is like the average cost of sieving per data that we have. And we also have in the key recovery CKR, which is the average cost per data pair that we need to try of the key recovery phase. So we can bound these things a lot of times. So we can say, okay, this is not going to be bigger than this, or we can make some suppositions, and then we can use this kind of formula when I said we want to include it in finding the distinguisher, finding also a bound that will tell us that it's possible that it will exist an attack with a key recovery leading to something better than exhaustive search. But actually, this is not what we want. I think we want something better. And when we arrive here, we can identify some problems. So we can see, for instance, the key recovery phase or the sieving phase also, that sometimes is a bit complicated, and we want to optimize them. So for this, we will extract this problem and have a look at it independently of the whole attack and try to find better ways of solving this. And this will allow us to adapt the formula with the new complexities that we have recovered. And also it's very important that once we have this, we have a look at the literature and we see all the improvements that could apply in this case or in a generic case, and try to see how they affect the complexity, introducing the new parameters depending on what we are doing new. And this will, again, adapt the complexity for the approximated complexity we have, and we'll get more and more towards a more accurate complexity of the full attack. And once we have done this, we can repeat the whole procedure for another type of attack and try to find similarities and try to generalize and to merge the things to provide something as general as possible, or have different cases depending on which are the things that need to be separated. So I think, as I said, the two first steps that are in blue have happened for some families, and the other ones are more rare, but they have been done sometimes, but I think they are very important and that they are needed for finding the optimal algorithms that we will need to apply in the end. So in general, I think before reaching an automatization that really includes all the ideas we have had and all the families of cryptanalysis that have been proposed, I think it's very important to do this work of first understanding what has already been proposed. There are some ideas that are proposed in a context that can apply to others. So this was also mentioned by Jose this morning. That happens very often. So really understand the potential of each technique and try to make the best out of it. So keep on doing the operational representation and approximated complexity that we have already started with the families that have not been treated yet, and doing all the remaining very complex parts of optimizing subproblems, including advanced variants and deriving more accurate complexities. And actually, I think for the optimizing subproblems, it's very interesting to go see algorithm experts sometimes, because there are problems that, not always, but sometimes there are problems that are known by the communities, or you can find some input of related things. And I think that it's a very interesting thing to do regarding type of generalization of cryptanalysis. And I also like to insist that I think there's a lot of literature to go through that, so try to read some papers that you haven't read yet. I should apply that myself also. And I think there are so many things that have been proposed and such nice ideas that sometimes are hidden inside an ad hoc cryptanalysis that I think it's worth it to go and try and fetch all of them. And so in general, so regarding this trying to reuse ideas, I think it could be interesting to keep in mind some things that are applied here or there, but not systematically and not most of the time, and that I think they can considerably improve the complexities of some of the attacks that we use. So for instance, I think having, when we try to design these algorithms, having a parameter that is the allowed per computation allowed, so the allowed per computation, I think it can significantly change which is the complexity that we will obtain in the end, and that is very interesting to have this in mind when we are designing the algorithms. And also that's so a lot of times when we cut the different steps of an attack, we cut the rounds in full, but it has been shown and used in many attacks that using not full rounds but partial rounds, and that one part is in one step and another part is in another, can considerably improve the complexity. So that would be very nice if we could try to use this in a generic way or maybe reusing more often gradual computations that are reused, and that way we don't have to do them again. So yeah, I think that are some nice things that should be included when doing this kind of generalizations and taken into account. So just to illustrate a bit like the scenario of symmetric cryptanalysis right now, we can represent it in this graphic where we have in the x-axis the primitives going from more traditional to more innovative designs. And in the y-axis, we have the cryptanalysis techniques going from well-known to new techniques. And I think that the open cryptanalysis platform that Thomas is going to talk about later, or the toolbox that we would like to propose, most likely will take into account all the algorithms that we could produce in the dotted space. And the ad hoc symmetric cryptography will increase or will be developed, and the platform, the toolbox, needs to evolve with this evolution also. And so just to show a little bit the different, how hard I think it will be to generalize the attack in the families. In the green part, I think it's maybe the easiest part because it's more understood things. And in the red part, it's maybe more complicated. And so Thomas' talk is about the open cryptanalysis platform. And Leo's talk is about innovative designs where we don't have any tools yet. And it would be interesting to see what he has to say about all the things that we need to do. So just to sum up, in my opinion, I think we need to transform the known cryptanalysis techniques with an algorithmic formalism through generalization and the long-term goal. But I think even if it's a long-term goal, we need to start working right now, as we are already doing. It's to reach a reference benchmark for evaluating the resistance to all known attacks. And this will allow us to have more time for finding new ideas and new ad hoc attacks that we will then have to generalize again, and never stops. And so yeah, as we are always getting more results, or some are more complicated to generalize, we won't be able to include everything in the toolbox, of course, but the toolbox will evolve with evolution. So that's all. Thank you very much. I don't know if you have questions or, yep.
Is there any question from the audience? So if not, maybe I'll break the ice with the. We should start accepting more systematization of knowledge papers, and that helps a lot. I have a small question. So we in cryptanalysis, we often consider attacks that are, let's say, slightly less, slightly faster than brute force. But they are very hard to verify in practice because, I mean, they're impossible to verify in practice, I would say. So what about, let's say, also studying algorithms that are, let's say, you can prove with the experimental results, so that, say, study the security of the cipher from the bottom instead of from the top. So I'm saying instead of studying algorithms that you can hardly verify because they have a complexity that is too high and you cannot experimentally, let's say, verify except verifying like single steps. What about studying algorithms at the lower level? So, for example, attacking a number of rounds that you can actually achieve and.
So the algorithms I'm talking about, they could be easy to verify because it's the algorithm. What you're saying when the complexity is very close to brute force is like an application or something the algorithm found, right? So an attack that is too high complexity. But if the algorithm works, finding generic attacks, you can apply it in lower versions to verify if it works correctly. So I think from that point of view, it wouldn't really apply on the generalization part. But I agree that it's very interesting also when cryptanalysis in general, I'm not talking about this, that not just look to very high complexity cryptanalysis and also study the more realistic options and see what is the security margin with this, right? I think it's very interesting also. Thanks, Emma.
Any other question? If not, we can thank Maria again.